Hello everybody and welcome to today's webinar. Thank you very much for joining us. I know quite a few people joined in early, which is great, so you're all ready, and there are a few more people logging in as we speak. But I don't want to delay anymore, so we're going to get started. And there's a little bit of introduction before the main part. So today's webinar is the Oracle Cost-Based Optimizer Basics. The main presenter for today is Randolph Geese. He's a member of the Oak Table Network, an Oracle ACE Director, and co-author of Expert Oracle Practices. You can also read a little bit more about the work that Randolph's doing and read some of his blog posts on oracle-randolph.blogspot.co.uk. Sorry. As always, I'm James Mercer, the creator and editor of allthingsoracle.com. I'm the Oracle Tools Product Marketing Manager for Redgate software. So before we start with the presentation, just a few points here. Everybody will be on mute for the duration of the session. It would be great to have everybody talking, but we've got an awful lot of people here today, and I think things would get a little bit confusing if everybody was able to talk. If at any time you can't hear us or the sound goes, please first check your GoToWebinar audio settings and your own speaker settings on your computer. If you still can't hear us and you're confident that everything's correct, please type a message either in the chat box or in the question panel. There will be a full Q&A session at the end. We'll try and answer all the questions that we get coming in through the course of the webinar. So as Randolph comes to points or as you think of things, please type these in the questions box in the control panel in advance. Of course, you can do this during the Q&A session at the end. This session is also being recorded, and I will send details of where you can obtain the video after this session. So looking at today's agenda, I'm going to have a brief introduction to Redgate software before I hand over to Randolph to do the main presentation, which is, of course, Oracle Cost-Based Optimizer Basics. Then the Q&A session. I'll finish off with some contact details for both Randolph and myself, and then some details on the next webinar. It's good to see that every time I do a webinar, I seem to get more and more people coming back, so I'm really pleased that there's a loyal following to these sessions, and clearly the work that I'm doing is of benefit to everybody here. For those of you that are new to or haven't come to a webinar before, and you haven't heard of Redgate software, here's just a little bit of information about Redgate. So Redgate was founded in 1999. We're based in Cambridge in the UK, and we're an Oracle Gold partner. We've been training for, as I say, since 1999, and our products are used by hundreds of thousands of people, and most of the main organisations, the large companies, will use some of Redgate's tools. The tools that we've produced for the Oracle platform, the deployment suite for Oracle, are based on tools regarded as the gold standard in SQL Server database development and administration. They really are, our top tools, gone through years and years of testing and usability. We're confident that the feedback that we get is the tools are hitting the mark and really helping people out. As well as producing nice tools, one of the things that Redgate believes passionately about is supporting anybody that's involved with the technologies that we produce tooling for. We have lots and lots of resources on the SQL Server and the .NET side where we produce tooling for, but also on the Oracle side, of course, as well. So I set up and I manage allthingsoracle.com. Program of regular webinars, some great sessions coming up, and I'm aiming to bring you a webinar on a Oracle development or Oracle database administration topic every couple of weeks. So please check out the webinar program, the upcoming webinars after this session, and of course we give away a number of free ebooks. You might have seen the information at the beginning of this webinar about our latest ebook. I'll be able to provide some details to that in the follow-up email to you as well, but we're at the moment giving away Expert Oracle Database Practices, which is an ebook by Tom Kite. And I think Randolph's going to mention that as well, but you will be able to download a free copy of that ebook from the Redgate website. Okay, so I'm going to hand over to Randolph now for the main part of the presentation. Hopefully this will go smoothly, but please bear with us if we have any little technical hitches. So over to you, Randolph.
Yeah, thanks, James. Welcome also from my side here from lovely Germany. This is not yet what I wanted to show you. So yeah, so that looks better now. Welcome to this webinar. Thanks for taking your time. I will try to cover the key concepts of the Oracle cost-based optimizer today. So although this is partially specific to Oracle, in fact most of these key concepts should apply to most relational database systems. You can see here my contact details again, like my blog where you can read my blog posts, and also my email address where you can reach me. Just a very quick introduction. I'm an independent consultant, and I'm actually available for short-term and short notice consultancy work, in particular in-house workshops about the cost-based optimizer, and also performance by design, application performance, and what you need to consider from database point of view. And also, of course, performance troubleshooting if you have any problems with the your already existing application. I can also be of help in sorting out things, why things might not run as smoothly as you expect. As already mentioned by James, I'm also Oracle ACE Director, which is an acknowledgement by Oracle for my contributions to the Oracle community. I try to post frequently on the Oracle technology network, on the OTN forums, and as I said, I also do some regular posts on my blog. I'm also a member of the Oak Table network. Maybe you have already heard of that. That's an informal and independent group of people believing in a scientific approach towards Oracle, so that you always try to show what you do so that others can discuss that, rather than simply stating some things without any proof. Well, yeah, I'm also a co-author of Expert Oracle Practices, as you can see, which is the one of the books that is by A-Press from the Oak Table network, and I've contributed 2 chapters about performance troubleshooting and performance monitoring. Right, so today, as I said, I'm focusing on the key concepts, but the point here is that these key concepts can be used for both. You can use it for proactive performance by design, and I will also touch on that a little bit during the presentation. And you can use basically the same knowledge for troubleshooting if you want to, if you already have something in place and you need to troubleshoot and understand why something doesn't perform as expected, then these key concepts should also be of help to you. But the main focus will be here on the key concepts. Well, so what is the main information that I will try to bring across today? If you yourself were to find an efficient execution plan for a query, then there are actually 3 main questions that you need to ask. The first question is how much data and how many rows, what data volume you have to process. The second important question you would have to ask is where is the data, which means is it scattered or clustered together? And the third question you would need to ask is about caching, and I will explain the meaning, what I mean by these questions in the course of this presentation. The main point, however, that you need to be aware of is that you need to know your data. So that is already one of the main things that you should keep in mind, that if you really want to understand what is happening and what is going on with the optimizer, then first of all you need to gain an understanding of what your data looks like. And then the second step might be to understand what the optimizer might get wrong about your data layout. Okay, so now you might ask, why are especially these questions so important? And the point here is that the optimizer, and in principle the database engine, has two main strategies that it can use. It can use the so-called, what I at least call, a big chop approach. So it basically tries to process the data all at once, or it can use a small chop approach, where it tries to access a subset of the data in an iterative fashion. So it runs basically in a kind of a loop. And this usually involves some kind of pre-ordered or pre-clustered information, like an index, that allows hopefully an efficient access to this subset of data. Now, these three questions basically allow you and the optimizer to find out which of these two approaches are more efficient in your particular situation. For there are just a few extreme cases, like you want to pick a single row out of million of rows via a primary key lookup, then it's very likely that the small chop approach is fine. So in the extreme cases, things should go fine. But if you actually have something in between, there's a huge gray zone, basically, where both approaches might be applicable, and therefore it turns out that you need to really answer or find the answers to these questions, which of the two approaches are really appropriate. So in particular, for the small chop approach, you need to know how often you have to run the small chop approach. So that is basically the question about how many rows, how many times. And there is a second contribution to the efficiency of this operation, that is the clustering and caching, that basically determines how much effort you have to put into each iteration. So both things together tell you how much work you have to put into your small chop approach. And on the other side, you have the big chop approach. For the big chop approach, you need to know how much volume you have to process and how much data. And of course, the volume and the data is also determined by the how many rows question. So this is where these things come together. So these are the main two strategies. You need to find out, can I find a very efficient small chop approach where I basically can access the data iteratively, or is it better to go for the big chop approach? And it might not be surprising that the cost estimates of the Oracle cost-based optimizer are actually based on asking the same questions. But there are two very important, significant differences how the optimizer approaches these questions in comparison to what you as a human being, how you can approach these questions. The first difference I already mentioned here, because it might be surprising to you that not all of these questions are actually handled in the same way by the optimizer. It doesn't cover all of these questions to the same extent. The how many rows, how much data, and what data volume is quite good covered by the optimizer. But in particular, the clustering and scattering questions, or where is your data located, is only partially covered by the optimizer. And the caching aspect is actually not covered at all by the optimizer, so that's another interesting point that I will come back to later. So this basically means that sometimes the optimizer might not be aware of some of the aspects of your data and your application that you are aware of, simply because the model of the optimizer, at present at least, doesn't cover these aspects. So that's already an important point to keep in mind. The optimizer doesn't necessarily understand the data the way you might expect it to understand it. So let's start with the first important question, that is how many rows. The question how many rows or how much data basically can be broadly divided into these three categories. You have the so-called single table cardinality, and you have the join cardinality, and you have some more things like filter subqueries or aggregations that again can be important to your execution plan. So these fancy keywords cardinality and selectivity I will mention a couple of times in the course of the presentation. Cardinality is just another word for number of rows, so that's the cardinality, and the selectivity basically means the filter ratio, so basically how many rows will remain after filtering or after joining. So that is basically what is meant by selectivity. These are the main things that you need to have in mind when thinking about how many rows. The single table cardinality is actually a pretty straightforward thing, because it basically talks about what is the selectivity of the predicates, the filters that you basically apply to a single table. So if you look at the below picture, then you can see here we have filter predicates on both tables T1 and T2, and we also have a join predicate here that joins T1 and T2. And the single table cardinality is basically just about those predicates that apply to a single table. So for example, for T1 table, you can see here that's just these two filter predicates, and for the T2 table, that's likewise the same here. Now, the point is that it's really as simple as that you can also verify this single table cardinality by simply running a select count star from the table using exactly these filter predicates. So for the T1 table, this would be select count star from T1, where T1 attribute 1 equals 1 and T1 ID greater than 0. And likewise for T2. And as I said, it's just about what do you have as base cardinality, so how many rows do you have in this table T1, for example, and what is the resulting cardinality after you apply these filters. So that is really straightforward and simple to check. You just need to find out which predicates apply to which table, and then you can basically verify that yourself. So although this might be very straightforward and simple, you might be surprised that the optimizer actually does have some problems coping with different kind of challenges that can be in your data, and so the optimizer might not have really a good understanding of even these simple and straightforward single table cardinality. I've noted here a few of these challenges, so I won't go into the details of each of them. It's just that you are aware of that there are a few of them, and depending on what your data looks like, you might have some of them, one of them, or just maybe even a combination of all of them. So in order to show you what this a very important aspect of this single table cardinality, I will now run my first live demonstration, and I've made up a simple story, a made up story. So what I do is here I simply run a two-table join that I will prepare now here, and we will have a look what this is about. Suppose this simple two-table join that I run here is actually a very important.
Hi Randolph. Sorry for
yes, James.
Sorry for jumping in there. The sound has gone quite low, and it does seem to go up and down a little bit. So we missed the beginning part of this live demo.
Yeah. So yeah, I see it in the panel. Let me check. What's the problem? So is it better now?
It's a little bit low, but I can hear you.
Still a little bit low, so I have to speak up a little bit.
Yeah, that's good. As you are now is perfect. Thank you.
Thanks, James. So sorry. So let me repeat that again. I have here just created a simple two-table join, where a simple two-table setup for my two-table join. And if you look at the data that I've prepared, then you could see that I have here actually a highly skewed data setup. So this table T1 that I've prepared here shows that in these two columns, attribute 1 and 2, there is a very popular value 1 and a couple of, I think, 1,000 or more very unpopular values. So this data set is highly skewed, and that is something that the optimizer should know about in order to understand your data if you actually filter on these attributes. So that is the main point here, that I have prepared a slight challenge for the optimizer. And again, I will mention that later on, but that is already a very important aspect, that I actually look at my data and try to know my data. So that is the point here. Right. So things have been prepared. I've created these two tables, and I will run now a couple of sample queries that should represent my more complex query. Of course, in reality, this query would be more complex, but it's sufficient to make the point here, because it already allows us to see a couple of important points. So what I've done now is I've run a query, and suppose this important report that I've made up is an end of month report, for instance. So you have to it is run not quite frequently, just at the end of the month, but it's very important because it's some senior level management report. And for a couple of reasons, it is run several times using different inputs, and these inputs, of course, this filter predicates, these inputs are on these columns that I've prepared with this highly skewed data distribution. So when I run the query here on this popular value, then you can see here in the resulting execution plan that so far everything went well, because the optimizer here understood that this is a very popular value. It estimated a lot of rows, like 800,000 rows, which is in the right ballpark. It's close to the actual 900,000 rows. And therefore the optimizer opted for the big chop approach, what I called big chop approach in the beginning. So you can see here this big chop approach, because it started all these operations, this join operation, this hash join in this case, it's just started once. So it basically read all the rows from this table and started the hash join joining to the second table. So that worked out fine and the performance was okay. And likewise, if I run a similar instance of the same report, but I use different attributes that are not that popular, then you can see that the optimizer actually opted for the small chop approach, because now you can see that it actually used a loop approach, where by using an index access it only accessed a subset of the data. And again, the performance was okay. The estimate was not really very precise, but it was in the right ballpark, so that the optimizer chose the right approach. So you can see here that it is estimating one row where we actually have 10 rows, but you can see here the iterative small chop approach, because this part of the execution plan was started 10 times. And the reason why I can see all this information, just to have that mentioned, I've activated here a special code path, additional code in the Oracle database engine, where it runs so-called row source statistics, where all this information, how many times have things started and so on, are actually measured by Oracle. And of course this means additional code paths mean additional overhead. So this means that things will be slower with this setting active. Now, so far, as I said, everything is going fine. It looks like that either deliberately or accidentally the developers have made everything correct. No one complains about the performance of these reports, and therefore there is one point that should be mentioned. If we look closely at this small chop approach here, then you might realize that actually the picking up 10 rows from a 1 million row table is here done via a full table scan. So that is not really that efficient, but since no one complains about it and the performance of these end of month reports is fine, no one bothers to change this. So we are just fine with that. Now suppose there is a change request coming. So now different data might have to be processed in the future. So the developer actually decides that it now has to change the query. And if you look at this output, then you can see that the developer might actually think, well, I know there is no index on the T1 table, no one has complained so far, so if I now change the query so that I need to apply these functions to these columns, because I have this change request where I might have to treat different data going forward, no one will probably see a difference, because a full table scan is the only possible access method, and therefore applying the functions won't prevent any index usage. So that's something that the developer knows about. If I apply a function then to a column, then I might end up with a full table scan instead of an index access, because the function basically prevents the index usage. So well, since there's only a table access full possible, that's fine. Looks like a very innocent change, and we can see it here confirmed, table access full, and if I use the functions instead, I still get a table access full here. Well, all right, so the change goes into production. We can even see that if we look at the data distribution, with the change in place, so that we use the functions instead, we still see the same data distribution. So everything looks fine to us. It's like before, so probably not really a problem. Let's run the query with the functions. And guess what? Of course, now the next end of month report, some trouble here because the report is not coming back in a reasonable amount of time. So the important points here from this presentation is that the optimizer by default does not look at the data. It doesn't look at the actual data. Since the optimizer is has to do the optimization as quickly as possible, it only bases its decisions on the available statistics by default. So if something is not visible to the optimizer by looking at the statistics, it simply might do some very bad estimates. So the basic mantra that you have to apply in such cases is, although things might be obvious to you, these things might not be obvious to the optimizer. The optimizer only looks at the statistics, and if your data and the query and the question that you ask is not obvious to the optimizer via the statistics, then the optimizer is basically lost. And this is basically what is happening here, that the optimizer is basically not getting the right picture of the data simply by applying these functions. Now the point is, as I said, it's still a full table scan very obviously, because T1 doesn't have any suitable index, so a table scan remains a full table scan. Why is then this plan, this execution of this report running so badly? So the point here is that if you think about your statistics, you have to consider not only if they are up to date and fresh. Of course, stale statistics can be a problem, and in particular if you have large amounts of data with partitioning and so on, this is really a challenge to get the statistics refreshed in a timely fashion. But it doesn't matter how fresh your statistics are. If the statistics aren't representative for your data and your queries, then it doesn't matter how fresh they are. So what has happened here in this case is that the optimizer has basically lost track of this highly skewed data simply because this function has been applied. And as you can see, it is still running, so we really seem to have a problem here. And I don't know if you know this, but you can actually, if you ever ask yourself whether you can really, if you can cancel a query that is running in another session without really killing the session, then this is actually possible. And I have a corresponding script on my blog. You can just search there for cancel a query running in another session, and you can basically download the script here, and it allows you to do exactly this. And since I have the problem here on the Windows that I cannot simply press Ctrl+C due to implementation details how SQL+ works under Windows, I will now use this nice script here, and hopefully my other session will be cancelled without being killed. And we can see here now it ran for 4 minutes and obviously wasn't still completed. And let's have a look now what actually has happened. So the problem is that, as I said, the optimizer didn't understand that we still have the same data distribution as before because the truncate functions have been applied to these columns. So instead of the actual 900,000 whatever rows, it just estimated 100 rows to be returned. So the developer was right in the point that the full table scan is still a full table scan, but the problem here is that the full table scan is still a full table scan, but the number of rows, how many rows, this question was misleading the optimizer, because it now thought only 100 rows will be returned, and it therefore opted for the small chop approach. So this is a very, very important conclusion for this single table cardinality. The single table cardinality, although it is called single table cardinality, can basically influence the whole execution plan. If you have a wrong single table cardinality estimate, it can ruin your whole execution plan. So this is a very important point, and it can be verified very easily by running simple select count star queries. Right? You can here see in this so-called predicate information section, you can see what filters are applied to this particular operation here, and you can run a simple select count star to verify whether the estimate of 100 rows is in the right ballpark or not. And you would find out in this case that although the table access full is still the only access path possible, that the number of rows question is answered incorrectly by the optimizer. And if this is incorrect, if the estimates of the optimizer are incorrect, it is very likely that the resulting execution plan is wrong, or at least inefficient. So that's basically the upshot of the single table cardinality. You have to ensure that the single table cardinalities estimates of the optimizer are in the right ballpark. Otherwise, it's very likely that the resulting execution plans will cause trouble. And therefore, since it is that easy to verify, this is basically your low-hanging fruit if you think about optimizer problems. If you address your single table cardinality issues, it is very likely that you already eliminate the most common problem for bad execution plans. And by the way, there is a wonderful feature of the optimizer that is called dynamic sampling, where the optimizer can actually look at the data and run a small sample on your data. And in cases where you can afford the additional overhead that is caused by this actual sampling of data, it can be very beneficial to use this dynamic sampling feature. And I have actually started a series on allthingsoracle.com where I discuss different aspects of this dynamic sampling. So you might want to have a look at that if you're interested, how you can get your single table cardinalities right. This doesn't mean that dynamic sampling is always the right tool. It depends, but it's just that you are aware of that this is available to you, that you can actually run this, use this dynamic sampling. And a final note on the single table cardinality and the how many rows question in general. If you use Enterprise Edition with the Diagnostic and Tuning Pack license, then there is this SQL Tuning Advisor available, and this Tuning Advisor actually does run the query partially and looks at the actual cardinalities and compares them to the estimates of the optimizer. So that's again a very important pointer, that knowing the actual data is a very important point, and that is basically what the optimizer does with this so-called offline optimization. But it is measured in minutes, so you can get an idea why the optimizer by default doesn't look at the actual data, because it simply means too much overhead and takes too long to do the actual optimization. Right, so again, the important conclusion for the single table cardinality is that its impact is not limited to a single table. It can influence the whole execution plan, and it is simple to verify. So at least for your critical queries, you should make sure that this so-called single table cardinality is done correctly by the optimizer, or at least in the right ballpark. Okay, so the second point about the how many rows questions is the join cardinality that I would like to cover, and here are just a few important points about joins. And the first important point about joins in Oracle and probably most other relational database systems is that it joins at most 2 row sources at a time. So if you have to join more than 2 row sources or more than 2 tables, then multiple join operations will be required. And the first problem here is that you can end up with a multitude of possible join orders, and therefore this makes this already non-trivial task to find out what is the most efficient join order if I have so many different possibilities to combine the different tables. So if you look at a tree shape of a typical execution plan, this is for instance a simple 3-table join that could look like that. Then you have the join operators here, and the join operators will either join actual tables or they will join the result of other join operations. So it is basically simple as that, and you can see from the layout here already there is only 2 row sources involved in the join operation. So again, what is the challenge for the optimizer with regards to joins? One of the challenges is getting the so-called join selectivity right, which means what is the filter ratio of the join. And the problem here is, again, that this is a non-trivial task, because a join can basically mean anything between returning no rows. If I just join 2 row sources, it might result in no rows, or it might be anything between the no rows and the Cartesian product. So if I join 2 things, then maybe the result is 0 rows, or maybe the result is 1,000,000 rows in this example, where I simply join to 1,000 row sources. So that's again not really a trivial, a simple task to determine what is the actual join selectivity. So that is one of the challenges, and that can be really a bit tricky for the optimizer. And then we will see here in this case, even if the join selectivity is estimated correctly by the optimizer, the resulting join cardinality, so they estimate how many rows will be returned by the join, can still be incorrect if the inputs to the join are estimated incorrectly. And that is exactly the explanation why a single table cardinality estimate can echo through the whole plan. So if the single table cardinality is incorrect, even if the optimizer gets any join selectivities right, the resulting final number of rows that is estimated by the optimizer is still influenced by the inputs, the filtered cardinality of the row sources that are joined. And that is exactly the reason and what happened in my demonstration, that the input to the join was incorrectly estimated by the optimizer, and therefore the resulting cardinality estimate was simply way off and was incorrect and had disastrous results to the resulting execution of the query. And there are various challenges again for the optimizer. You can have all kind of different join methods like anti-joins, where the optimizer often is capable of transforming your not exists clauses into joins. And you can also end up with non-equi-joins where you do range comparisons. These are all things where the optimizer has really potentially problems getting the join selectivity in particular right. And likewise, even for the most common form, the simple equijoin, inner equijoin, you still can have a lot of problems that cause the optimizer trouble again with coming up with the correct number of rows. We are still talking about the how many rows question. Okay, so let's do another demo to show you what problems you might end up with this join cardinality. I see that I again have problems with the microphone. I'm really sorry for that. I will try to fix that. Hopefully it gets better. I don't know. So again, I will start with a very simple setup where I just create two tables that will be joined, and you can see here the data distribution. I will talk about that in a minute. And we can see here again that we have let me just start this again, because it was missing the echo on, so that you can see what was actually going on. So I create one table that has a foreign key to another table, and it's a very simple setup. We have one table with 1 million rows with a foreign key to a table that has just 1,000 rows. And we even have valid constraints in place, like primary key and foreign key constraint between these tables. The point here is, however, that the foreign key in this one table that has 1 million rows is again highly skewed. So I have one row that is one value that is very popular, this foreign key with the ID 1. And we have also the parent table, basically, where we join to, where we have the matching data. And these are just a subset of the data of each. But you can already see that we have here this foreign key that is rather popular, and we have the other rows that are, again, not very popular. So if you now think about if I now join these two tables and I filter on the parent table, right? Then you can see that it is hopefully obvious to us, if I filter on this row here in the parent table and I join to this table here on this foreign key, that the majority of this 1 million rows will be returned, because the foreign key 1 maps to more than 900,000 rows. So if I now ask the optimizer about his estimates of exactly this query, where I filter on the D table for the description 1 and join to the T table on this foreign key and the ID, then we can see here that this estimate on the D table is correct, that it says there's one row, which is obvious because there's a primary key and I do exactly query for a single row. But we can see that the final cardinality is incorrect, totally incorrect, because it estimates just 1,000 rows. So if you have watched closely what I've done, then you might have realized that I haven't generated a histogram on this table yet, and you are right. So I haven't told the optimizer about this data skew yet. So let's have a look here and generate a histogram. and then let's see what happens now. Okay, so just to give you a confirmation, that is here a problem. I have asked the optimizer how many rows he expects when I just ask for this foreign key equals 1. And you can see here it says just 1,000 rows simply because I have 1,000 different values in 1 million rows. So on average it estimates 1,000 rows per value. So that is of course incorrect. So I will now generate a histogram, which I have done here with this gather statistics, and we can now see here that we have a histogram. And if I now ask for the histogram information, I see that the optimizer correctly sees that the foreign key 1 is very popular, and I see the confirmation also in this explain plan output now that 900,000 rows are estimated if I filter on the foreign key 1. So I have now a histogram in place on the foreign key. Now I repeat my query where I filter on this very popular description 1. So the problem here is, as you can see, although we have verified we have an histogram in place and the estimate on the table D is correct, the estimate of the join cardinality, the resulting join cardinality, is still incorrect. And that's really an issue. So join selectivities can be tricky. And here again the problem is the optimizer doesn't have a chance to look at the actual data. So what seems to be obvious to us, that if I filter on this single row and I join to this very popular table, join to this very popular foreign key in the table T, it's simply not obvious to the optimizer. The optimizer only sees that I filter on a single row in table D on the description 1, and it doesn't have a clue that description 1 maps to this very popular ID 1. That's simply not available from the statistics. So that's just a point that join cardinalities and join selectivities in particular can be a tricky thing. And unfortunately, since you have that many different join possibilities, some of these nice tools like dynamic sampling and other things that you can use for the single table cardinality issues are not available for the join selectivity and join cardinality issues. So sorting out joins can be a tricky thing, and again you need to be aware of the fact that what seems to be potentially obvious to you as a human being is not necessarily obvious to the optimizer. Okay, so that is what I wanted to say about the join cardinality. Of course, if these resulting how many rows question, the answer to this question is wrong, again you might have the same problem that anything that is done based on that number of rows estimate can go wrong. So again, the optimizer might opt for the small chop approach, although the big chop approach might be more efficient, or the other way around, it might opt for the big chop approach where you would need a small chop approach in order to sort things out. Well, what I've discussed so far is the question how many rows, what data volume. But in order to understand what is the efficiency of the small chop approach, you also need to think about what amount of work is required in order to do each iteration of the small chop approach. And this is what is meant by this data scattering and data clustering. You have to think about that the data is organized in blocks in the database. So a lot of blocks can fit into a single, many rows can fit into a single block. Therefore, depending on whether you have to access many different blocks for many different rows, or if the data is clustered in a few blocks, can make a tremendous difference in terms of efficiency of the small chop approach. And here's just a picture to make you aware of this difference. This is should represent a typical index range scan operation. So on the upper hand, in this area, you can see the index tree. This should be a part of the index tree. This is a B tree index, and you can see the table below here. So if we do a typical index range scan operation, then we walk basically the index from the root block to the branch blocks, to the leaf blocks, and that is usually a very efficient operation, because according to the access predicate that you use for the index, it just depends on the height of the index. So you start at the root block, then you have one or more branch blocks, and finally you arrive at the leaf block. From then on, the operation is very simple from the index perspective. You just have to walk this linked list of leaf blocks without having the need to do anything else with the branch blocks. So this index scan operation itself is very efficient. The problem, however, is that for every row that you identify in the index, you have to access the corresponding table block. And in this example here, you see that I have to jump basically for every row to another block. And for instance, in worst case, if I have identified 1,000 rows in my index, I have potentially to visit 1,000 different table blocks. And if I have the worst case that these table blocks have to be read from disk, and I assume a typical random access time of 5 milliseconds, then I end up with an estimated runtime only for these 1,000 random table block access of 5 seconds. So that's just 5 seconds for accessing these 1,000 random blocks. In contrast, if you look at this picture again, I walk the index, and now I do the same index range scan, but I access the same number of rows in the table, but the rows are basically in the same table blocks, and I access over again the same table blocks. Then I can do the same amount of work finding 1,000 rows in the table by, for instance, just visiting 10 table blocks, because these rows are clustered together in the same table blocks. And that is essentially what this data scattering and clustering is about. And if you compare now the 50 milliseconds to the 5 seconds for the same number of rows that you have identified via this index range scan table access, then you can imagine that it can make a huge difference. So this is basically the second part of the calculation, how efficient your small chop approach can be, because you have to consider how many table blocks you might have to visit randomly in order to pick up the data. And that is the data scattering, data clustering issue. This also means that if you know about this clustering or know about this scattering, that it might be more efficient to access 1,000 rows that are clumped together in 10 blocks instead of visiting 200 rows that are spread across 200 blocks. So it might be more efficient to process more rows if they are clustered together than processing less rows that are scattered across many different blocks. So that is a very important point in order to determine how efficient your small chop approach can be. And that is basically the second part of this how much work does the small shop approach cause. This can have all kinds of side effects. If you think about caching, for instance, if you have that much collateral data that might not be of interest to any other concurrently running queries, then you might have a problem with the caching, not only for the query that we are just talking about. You might also have a problem with other queries that run concurrently that compete for the buffer cache. You might even have impact on concurrently ongoing DML operations that manipulate data, because there might be a high demand for free blocks in the buffer cache, and therefore the blocks that are dirty and have not been written yet to a disk might have to be written very quickly by the DB writer from database engine side, which puts additional pressure on your I/O subsystem. So I just want to make the point here that it really can have all kind of side effects if you have a query that is running with this small shop approach, but the data is very scattered. And this is just a note regarding the performance by design point, that most data that is arriving in an OLTP system at this around the same time is usually clumped together in a heap organized table. But it really depends on the physical organization of your data. Just for example, if you use a hash partitioning for your heap organized table, the rows might be spread across different heap different hash partitions of your heap organized table. So what has been clustered together in a non-partition table might now be spread across different blocks in the hash partition table. So these are all things that you need to consider. And the point here is that you basically not only have to consider what are the effects of doing such different physical implementations and physical design. You can even use that proactively, that you say, I might use different physical organizations of the data if I know that I have very important queries and very important processes in my database, in my application, that might benefit from particular clustering of data. So you have all kinds of options and different things that can influence the clustering and scattering of data. I've already mentioned partitioning. There are also clusters in your to your availability in Oracle. You can have index and hash clusters that basically pre-join data. You can have index organized tables that basically use an index-only way of storing data, so there is no table access in that sense anymore. There's no heap part of your data anymore. It's all data is stored inside the index. And you also, for the heap organized tables, you can still make a tremendous difference by a very clever index design, by using composite indexes or function-based indexes. So there is a reason why the Oracle internal data dictionary uses clusters all over the place. So ideally, and already at design stage, you should know your data, you should know the critical queries, critical processes, and you may be able to take advantage of some of these options that are available to you. But of course, you also need to understand the trade-off, the downsides of, for instance, using a hash cluster or an index organized table. Otherwise, Oracle would use them automatically. So you have to understand what are the pros and cons of using the different physical organizations. There's another point that by default, the automatic segment space management that has been introduced in Oracle 9i has an influence on the way the data is actually scattered or clustered together. And since by default you should use the ASSM, the automatic segment space management, you should be aware of this fact that, in fact, ASSM does influence the way the data is stored in a heap organized table. So it actually addresses this point that you may have contention by concurrent processes that try to access the same block. So therefore it by default spreads data across several blocks that are inserted concurrently. So this can already have an influence on the way the data is scattered and clustered. And here is just an idea, the same picture again. What if I do not have a table access at all? If everything is stored in a covering index or in an index organized table, then you might have a tremendous difference in performance if otherwise you would have to do all these random access to your table blocks. So that is just the idea that this performance by design can make a tremendous difference. Now, what does the optimizer know about this scattering and clustering? The optimizer does know about this clustering and scattering only by the way of the so-called index clustering factor. And the index clustering factor is just a single value that basically represents how well the table data is clustered when comparing to the order that is represented by the index. So basically what Oracle does, it walks the index in the order of the index that is defined by the index definition and looks at each row whether a different block will be accessed or not. And each time, by walking the index, each time the block changes, the clustering factor will be increased. So basically the clustering factor can be as low as the number of blocks that are covered by the index or as high as the number of rows that are covered by the index. If the clustering factor is low, so that it's close to the number of blocks, then the data in the table is very well clustered in comparison to the order in the index. And if you have a high clustering factor, then the data is highly scattered. So that is what the optimizer knows about. If you think about now this ASSM thing, then the problem is that the data is spread across a few blocks, so it is still clumped together in a few blocks. But if you think about the logic that you every time you walk from row to row and see a different block, it doesn't cater for the fact that you might be jumping across the same few recent blocks. So that is a problem that the clustering factor can in fact be incorrect or not really representative if you deal with the ASSM feature. So I do have a demo for that, but we do not have the time to look at that because I'm already here talking for close to an hour. Right, so this is the point that I try to make. This is again the same index range scan operation, so we walk the index, that is all fine. We find the first leaf block of the index, and then we do the index range scan, walk the different entries in the index, but as you can see, we basically jump back and forth between the same blocks, and that is the problem with the clustering factor that can be influenced by such a clumped together thing that the blocks are basically the same, but I jump back and forth. It's not necessarily 2, it could be more like 4, 5, 6, 10, whatever. But it makes a tremendous difference because the blocks that have recently been visited are very likely in the buffer cache, and therefore you do not have this impact of the physical random access. So if you end up with a very high clustering factor, but well, it's not that bad as the clustering factor suggests. The other point that I wanted to make about scattering and clustering is the problem that the optimizer doesn't have really a clue about what is the clustering if you join tables. So if you have a small job approach where you join tables in a loop, then the optimizer doesn't really know how good these intertable clustering looks like. And this is what we have seen before, the nested loop join. So we have the driving row source here above, and we have the index and the table that is joined. And if I walk now here this driving row source and I try to access the second row source via this nested loop, then you can see again here this picture where basically for every row that is identified in the driving row source, I walk the index and finally identify the row in the second table. I again have the problem that I jump for every row to a different block. So the table, in this case, these two tables are basically not really very well clustered in terms of the join. Now, the same operation, again, I walk the first table, I go through the index, that is basically the same operation, and here I identify the same blocks one after the other, so the data is very well clustered together. The problem here is that these two things are basically not aware, that the optimizer is not aware of these two differences, whether you have the one or the other approach. The optimizer simply doesn't know that. That is something that is not available from the statistics and is also not available from looking at the data. So the optimizer simply doesn't know about that. If you know about that, if you know your data well, then you might take advantage of this and therefore might have to influence the optimizer in its decisions because it's simply not aware of this fact. Okay, so, and for an entertainment, just to give you the idea, if I had the data pre-joined in a hash, in an index cluster, for example, then this operation could look like this. So rather than going from one table to the index to the other table, the data is already pre-joined, and that is probably a very efficient operation. Just to give you an idea what a tremendous difference this pre-joined cluster might make in terms of efficiency of the small job approach. So, and just to give you an idea, I have shown you the previous example where this query basically ran for a very long time because the optimizer used the small job approach and therefore the execution plan was suboptimal for this case. And let's have a look at that. If I give now you again the cost estimate, in this case I would like to look at the cost estimate. This is the cost estimate for our original bad execution plan. So you can see here still this wrong estimate of 100 rows, and you can see a cost of close to 5,000, which is easy to remember. So we have a cost of 5,000, and you remember that it took 4 minutes to run the query and it wasn't completed yet. Actually, it would have run for hours. And now I will basically recreate the second table, but this time I will create it in a different order, in an order that is corresponding to the first table. And if you look now at the result of the explain plan output of the optimizer with this different order in the T2 table, then you will notice that we end up with exactly the same cost. So although I have changed this clustering scattering between these two tables that are joined by the query, the optimizer doesn't really have a clue about this. So that's the main point here. It doesn't really know about this. But at runtime, if I now run the same query again with this inefficient execution plan, it should actually make a huge difference. So I run now again the same query, again with the same inefficient approach, but this time the data is clustered together. And it took 4 minutes and wasn't completed. Now it just took 12 seconds. And we can see here we have still this incorrect approach of the optimizer of estimating 100 rows, but actually it has to do the small chop approach 900,000 times. So it was still a bad execution plan, but the main difference between the runtime of the first demonstration and this demonstration is that the data was now clustered together, whereas in the first demonstration I have deliberately crafted the data so that it actually was very scattered. And the optimizer, as we have seen from the cost estimate, doesn't really have a clue about this difference. So that was the point in the beginning where I said that clustering and scattering is only partially covered by the optimizer. There might be cases where you simply know a lot more about your data than the optimizer, and this is such a case if you have a particular scattering, clustering between tables. So that's something you can take advantage of. That's something that your optimizer doesn't know, and you may know if you know your data. So finally, a few words about caching. I don't have really to say much about caching. You already have seen that caching is closely related to this scattering clustering thing. So the difference, of course, is tremendous between logical I/O and physical I/O, so whether you can read data from the buffer cache or whether it has to be read from disk. But the point is, the important point that you need to take into account is that the optimizer doesn't really know about caching by default. It simply assumes that every I/O that it estimates will be physical I/O. So if you happen to know that a particular part of your data is very likely to be cached very well, like the most recent orders that have been processed in your system, then this is something that you might need to tell the optimizer about. That is simply something that the optimizer is not aware of. So that is just something that is important, that caching can make a huge difference, but the optimizer by default simply assumes everything is physical I/O. So that is something that you have to take into consideration also if you try to find an efficient execution plan. And it's again something where you might need to influence the optimizer because it's simply not aware of this. There are different ways you can do this. There is this optimizer index cost adjustment, optimizer index caching parameters, system statistics. So there is actually a lot to say about this caching and costing thing, but I just wanted to say here in this context that you have to be aware of that the optimizer by default simply doesn't know anything about whether part of your data is cached well or not. Well, yeah, there's one thing that actually Oracle obviously was playing with the idea of introducing a per object caching into the cost calculation, but it obviously hasn't made it into production, at least yet. It's not available, and you can see this if you look at the data dictionary. There are some columns like average cached blocks, average cache hit ratio, but they are not populated yet. And the optimizer also does have some special parameters that you could use in previous releases in order to activate a kind of beta mode where it tried to use some caching. But it's not there, it's not in production. Maybe it will come in future releases, but as of now it's not there. And just a final word on the caching is that that you are aware of the fact that even if you turn every I/O in logical I/O by caching everything in the cache, by putting all your table and indexes in the cache, usually won't be able to do this because you simply do not have sufficient memory. But even if you could, inefficient execution plans would still be a problem. They might not be that bad, but in the end, if you have inefficient execution plans, you might end up with contention and high CPU usage and still potentially poor performance because you might have too much concurrent access to the blocks, because Oracle simply has to serialize and coordinate access to blocks in the memory, and these serialized code paths would simply be called too often if you end up with inefficient execution plans. So even with very good caching, all the other things that I've mentioned with the how many rows, how scattered, how clustered is your data, is still a very valid point that you end up with efficient execution plans where the optimizer chooses the correct big job, small job approach so that it gets this right. Even with a very good caching, it's still important. So the wrap up for this session is that the cardinality estimates and the scattering clustering determine whether the big job or the small job strategy should be preferred. And if the optimizer gets these estimates right, then the resulting execution plans in the boundaries of the given access path, if there's a missing index, then the optimizer cannot create this index on the fly. But within the given boundaries of what access paths are available to it, the resulting execution plans should be fine. And in order to get an idea whether the optimizer gets it right or not, you probably have to know your data and the questions that you ask about your data. And again, you have to consider that what might be obvious to you is not necessarily obvious to the optimizer. So even if your statistics are 100% computed and just refreshed a couple of seconds ago, if these statistics do the optimizer not allowed to understand your questions that you ask about your data, then the resulting execution plans might be quite inefficient because it might opt for the small job or for the big job approach, where the other one would be more appropriate. All right, before we jump to the Q&A section, if you are interested in more information about these topics, I have just put together a couple of recommended reads that you might want to have a look at. And the first one that I would like to recommend is actually at Redgate's simpletalk.com, which happens to be the SQL Server stuff sponsored by Redgate. And there is an article by Jonathan Lewis designing efficient SQL, and it's basically picking up all the topics that I've mentioned here, and it's very fascinating to see literally how Jonathan designs a query for performance, and it also demonstrates how to use a visual approach in designing queries for performance. So you probably want to head over to SimpleTalk and read this article now that you have heard what I've outlined here with these basic questions that you should ask about execution plans and the optimizer, because it will give you further insights about how you can use this knowledge. Then you should, before you rush off and now start creating clusters and index organized tables all over the place, you should take one of your favorite copies of the Tom Kite books and read about the pros and cons of clusters and indexes, clusters and index organized tables and the other available formats that you can use in Oracle, so that you understand in which situations it might be reasonable to use clusters, where it might be reasonable to use index organized tables, or where you are just fine with the standard heap organized tables. So it's very important to understand these implications, because improper usage of clusters or index organized tables might just lead to all kinds of problems, and therefore it's very important to get here the basics right, and Tom Kite covers these basics in his books. Then another problem that I come across quite frequently is that people have problems in reading and understanding the execution plans, the explain plan output by Oracle. And it's surprisingly hard to find good information how you actually have to read and interpret these execution plan outputs. And the best description that I have found so far is in Chapter 6 of Troubleshooting Oracle Performance by Christian Antonini. And this is, by the way, one of the best books about performance troubleshooting in Oracle. Anyway, so this is a recommended read. And it's very important to get this right, so that even if you know your data and you have an understanding of your data, and you might think that you have an idea how Oracle should approach your query, the small job, the big job approach, if you cannot read and interpret the execution plan, then you are basically not able to understand whether Oracle has the same understanding as you have. So that is a very important point, to get it right, to see what does the execution plan actually tell you. So Christian does here a very nice job. As I said, I think it's the best description I've seen so far, and once you have gone through this, you will be able to read any kind of complex execution plan, no matter how complex it is. And then if you are in the position to really understand execution plans, then you might be surprised by some of the execution plans that you see. And here's just one of these examples. If you take this query here, we have a two-table join here, and we have a aggregate subquery here, and then you might start wondering, wow, how should I address this aggregate subquery? Looks like a complex thing, only to find out that the optimizer might have transformed your query into something completely different looking. In this case, it is a join, so it has transformed your aggregate subquery into a join. So you don't have to think about your aggregate subquery any longer, because the optimizer has turned this into a join. Or you might even end up with something like that, so that the optimizer has completely removed your aggregate subquery and turned it into an analytic function. So all of these query transformations that the optimizer applies to your queries are basically rewrites for performance. So Oracle tries to find logically, semantically equivalent forms of your query that might allow the optimizer to arrive at more efficient execution plans. So that can be quite confusing and surprising. So I just mentioned it here, that these query transformations are something that the optimizer very regularly applies to your query. So it starts rewriting the SQL that you put in, and you might end up with a completely different SQL that is then optimized by the optimizer. And with every release, Oracle basically improves this query transformation capabilities. So every release, like 11.2 or so, adds more capabilities. So the more recent your Oracle releases, the more likely it is that you end up with something, with a SQL that is different from what you have originally submitted to the database. Then another recommended read is SQL Tuning by Dan Tao, which basically teaches a formal approach how you can find an efficient execution plan yourself. Again, this is about a visual approach that you can basically draw your query and find efficient execution plans. It focuses on robust execution plans in an OLTP environment, so it's mainly about this small job approach, but it's still a very interesting read, in particular how to use a formal approach to draw your queries. And then another very important topic is good index design. Here is a book that focuses on index design. It's not about Oracle only, it applies to many different databases, but again the same key concepts apply to most of the relational database systems on the market. So it's a very good read and also gives very good ideas what a good index design can make in terms of what a difference a good index design can make in terms of performance. And there's another good read about index design that is an online book by an Markus Wienand from Austria, Use the Index Look, and it's again focusing on the index design, but it also provides a lot of nice examples how you can use this efficiently. For instance, if you have Hibernate or if you have front-end languages like Perl. So that is also a very important point, that developers get an idea what they can take care of, what they can take advantage of in their particular front-end code. It's also available as a free ebook. Yeah, and finally, of course, if you are interested in optimizer, cost-based optimizer things, all the things that I've outlined here in more detail, you can find in Jonathan Lewis' book, Cost-Based Oracle Fundamentals. It's already 6 years old, but of course still the best book about the Oracle optimizers, and covers all these key concepts that I've mentioned here in a great detail. And I think that's it. James, then I'm over to you.
Thank you very much, Randolph. Before we go on to the Q&A, I noticed a few people have left. Maybe it's because it's a little bit longer than you expected, but I hope the content has been useful for you. I've certainly enjoyed it so far. Before we actually go on to the Q&A, I very quickly just want to take control of the screen and show you where you can actually get hold of the Tom Kite book that Randolph mentioned. Okay, so this was the book that I showed at the beginning of the webinar. If you joined a little bit late, then you would have missed this slide. But we are giving away copies for a limited time of the second edition of Expert Oracle Database Architecture by Tom Kite. And you can see the URL of where to download this book at the bottom there. Okay, so I'm going to pass the screen back to Randolph now. As I mentioned at the beginning, this webinar has been recorded. You will be sent details of where you can obtain the video recording afterwards. But please stay on the line with us, because we've got quite a lot of questions, and I hope you've got some questions yourself to put to Randolph now. And this is always an extremely useful part of the presentation, so any areas that you want clarifying, this is your chance. So Randolph, I'm just going to hand the screen back to you now.
Yeah, thanks.
Okay, so just bear with me a little bit. So I'm just going to bring the question panel up. So we had quite a few that have come in during the course of the presentation, which is great. Okay, so we have a question here from Kelleen Potvin. Thank you, Kelleen, for your question. So the question is on, should dynamic sampling, is dynamic sampling, it shouldn't be a replacement for statistics, but many think so. Should be an addition to using it. Sorry, it's slightly confusing the way this question is written, but basically, if dynamic sampling should never be a replacement for statistics, for those using it, they need to understand the parameter values. Does that make sense, Randolph?
Well, yeah, I think so. I think it's probably not that easy to answer, but in principle, I think the good answer is, of course, it depends. But if you have, for instance, a database system where you have mostly long-running queries, or even use parallel execution, for example, then Oracle 11.2 by default starts using dynamic sampling, because it assumes that the overhead at optimization time easily outweighs the potential performance gain at runtime when actually executing the query, because it assumes by looking at the data, actually looking at samples of the data, it ends up with better cardinality estimates and hence ends up with better, more suitable execution plans. So that is already pointing into the direction that dynamic sampling is very valuable if you have long-running queries that use, for instance, parallel execution. If you have, for instance, a system that runs a lot of queries, short-running queries that are supposed to use the small chop approach and finish very quickly, then the overhead of dynamic sampling might be inappropriate, and therefore you better rely on the statistics and try to get the optimizer with statistics that allow him to arrive at good estimates using the statistics. And regarding, sorry James, regarding the different parameters, that is something that I also address in this dynamic sampling series on allthingsoracle.com, so that you can get an overview and understanding what the different parameters, the configuration of the dynamic sampling actually means.
Fantastic, thank you. The next question from T. Austin, thank you. What role does the newer 11G extended stats play in the join cardinality? Is there some information about how columns relate to each other across tables?
Yeah, that's actually a very good question. Yeah, that's still not addressed actually by Oracle. So there is, even with the extended statistics, there is no information to the optimizer available regarding the inter-table information. So the example that I have shown, where even with the histogram in place, the optimizer did a bad estimate of the join selectivity and join cardinality, cannot be addressed by extended statistics. So that is really a tricky thing, getting join selectivity estimates right. There is no real good thing that has been added in the recent releases that addresses this particular issue. So even with extended statistics, you can use extended statistics very well, very good for the single table cardinality issues, but you cannot really use it for the join selectivity issues. So for single table cardinality, it's a very, very good thing. For join selectivity issues, it's not really of big help.
Great. Thank you, Randolph. Your sound went a little bit quiet again.
Yeah, I know. Thanks.
Okay, that's good. Okay. Next question from Simon Kumar. Thank you for this. If we created extended table stats on trunk, in brackets, COL, then would it have solved the incorrect plan issue in example 1?
Yes, exactly. That is one of the options that you have. If you generated extended statistics on this function, then the optimizer would come up with a better estimate. In fact, you can use, for instance, function-based indexes in pre-11G releases to arrive at the same functionality. But even better, the thing that I usually recommend is to review whether you really need these kind of functions, because very often the same expression could be well, the same logical thing could be expressed using a different expression that does not use the function or expression on the column, but uses some kind of different approach that avoids this. So I think the first thing is to review whether you really need this function, and if you are really sure that you need to use this function, then you really need to use some kind of extended statistics or function-based index approach in order to support the optimizer. But the first thing that I always recommend is review whether you can rewrite this using a different approach where you do not need to apply the function. Then in this case, if you do not apply the function, the basic column statistics can be used again by the optimizer and you should be fine. So that is basically the two-phased approach here. Of course, you might have already existing applications where you cannot simply rewrite the SQL, and in this case, the extended statistics approach is a very good one.
Thank you, Randolph. So I think Suman has added a couple of comments, so just bear with me here. Okay, on to the next question from Kumar Majuri, so thank you for your question. So he's talking about the right join order. So I understand the explanation and problem it will cause if the optimizer doesn't pick up the right join order properly. Do you have any tips on correcting that?
Well, in principle, as I said, the most important point is, as I already mentioned, the low-hanging fruit, basically, that you have is getting the single table cardinality right in first place, because these can easily be verified, and they are simply the most common problems. So the single table cardinalities, as I said, will influence wrong single table cardinality estimates, will influence the join methods, the join order. So these are the things that you should sort out first, because these are the things where you can verify very easily. First point. Second point, you have a lot of different features at your disposal that you can use to address these issues, like for instance extended statistics and so on, dynamic sampling. So if you have sorted out the single table cardinality issues and you still see that the join order is inefficient, then very likely the join selectivity is an issue. Or if you have more complex queries that include subqueries, then things might get even more complicated. But I haven't addressed that in this basic introduction here. But if the join selectivities are then still causing issues, then things get a bit tricky, because it's not that easy to correct these join selectivity things. As you have seen, even by adding extended statistics or histograms, it doesn't really help in some cases, and then you might only have the chance to correct things by using hints or other options like the SQL tuning advisor. For instance, if you have the Enterprise Edition diagnostic tuning pack license, then you might have to use such approaches.
Great, thank you, Randolph. Next question is from Rahil Said, thank you. How do we cluster the rows in a few table blocks? Are there any storage settings whilst creating segments?
Yeah, well, as I said, basically in the heap organized table, you do not have that much control, since by definition the heap organization means the table row can go into any arbitrary block. If you really want to influence the clustering in your table, then you would need to think about options like using index or hash clusters or using index organized tables. These are the options, the obvious alternatives that you could use, and that will lead to a different clustering of your data. But of course, that's what I meant. You need to be aware of that this has some other side effects and other implications that you need to be aware of, and therefore you have to understand them, and you need to test in your particular case whether the pros really outweigh the cons of such an approach, because the point is that usually if you want to store your data in a particular clustering or ordering, then you will pay a penalty at data manipulation time. If you manipulate the data and modify the data, then Oracle has to work more in order to put the data into the correct place. Whereas with the heap organized table, you have a lot of options where you can get the data very quickly into the database. But then you have the problem that the clustering or scattering might be a problem. So that is the typical trade-off, the decision that you have to make in this case.
Thank you, Randolph. And following on from that, when using ASSM, what are the impacts on the insert and update statements?
Yeah, the ASSM that I've mentioned, the point is that ASSM by default addresses the issue that the data is, if you use, or let me start in a different way. If you use the old school manual segment management and you do not define any special free list and free list group settings, then by default all rows by all concurrent inserts will go into the same table block. So if you have only a few concurrent inserts, then this is not really an issue. But in a highly concurrent systems where you might end up with hundreds or thousands of concurrent inserts, this will cause a problem because Oracle has to coordinate the access to this block, and therefore it will serialize the operation. And hence you might end up with contention on this so-called hot block then. So if you have a highly concurrent system, then you need to do something about it. With the manual segment management in the past, you would have to fiddle with the free list and free list groups settings, which would end up with processes that insert the rows in different blocks concurrently. So you would basically spread the data across several blocks. This relieves the contention, but of course has the effect that the data is now scattered across several blocks rather than inserted into the same blocks. And it's exactly the same thing that the ASSM does by default. If you do concurrent inserts with ASSM, then the data will be automatically spread across different blocks. And hence you end up with data that is not that well clustered anymore as with MSSM, with the legacy manual segment management. The point is, however, that the data is still clustered, but in a different way. It is spread, it's clumped together across a few blocks rather than stored in the same block. And you still get the benefit of data that is clustered together, but Oracle has problems when it determines the clustering and scattering with the index clustering factor, because the measurement, how the clustering factor is measured, doesn't cater for the fact that the data is actually spread across a few blocks, and therefore the clustering factor potentially is measured much too high. So you end up with a worse clustering factor, although the data is still pretty well clustered, but it's not clustered in the same way as with the legacy manual segment space management. So that's just a point that if you ask yourself, why is Oracle not using my index, so that is one of these classic questions, then you might want to check if the clustering factor is actually representative for your data. And I have on my blog, let me check this, I have here a block note on the clustering factor, and you can use the queries that I've provided there in order to check if the clustering factor that Oracle has measured corresponds to the real clustering of your data. So you can play scenarios, what-if scenarios, and you can check whether the clustering factor determined by Oracle is in the right ballpark or not. It's also something that Jonathan Lewis covers in the cost-based fundamentals book.
Great. Thank you, Randolph. I've got a question here from Saeed Nizamuddin. I hope I pronounced that correctly, but thank you. He would like to know some examples of when you would use an index range scan or an index fast scan. Which scenarios would one be better than the other?
An index range scan versus an index full scan?
Index fast scan.
Index fast full scan, okay, right, thank you. Well, you have to consider that the index fast full scan is basically just a shortcut that Oracle can take for the big chop approach. So if Oracle determines that all the information that it needs to process can be read from an index rather than accessing the table, and the index is significantly smaller than the corresponding table, then it can opt for this index fast full scan, where it basically runs through the whole index and reads all the data from the index and ignores all noise, if you want to say so, all these root and branch block information and the row IDs that are stored in the index BB tree will be ignored, and it runs through the index and uses it basically as a skinny copy of the table. So the index fast full scan is basically just a shortcut an optimization that Oracle can use for the big chop approach. If you want to have this small chip approach where you selectively access only a subset of your data using this pre-ordered information in your index, then you would use an index range scan.
Great, thank you, Randolph. The next question here from Thomas Phillip. Thank you, Thomas. What other ways we can avoid the single stroke join table cardinality confusion an optimizer has? When you say cluster data, do you mean the cluster table?
I'm not sure I understand the question. Can you repeat it, James?
Yeah, sure. So one of the ways, so what Thomas would like to know is the ways to avoid the single stroke join table cardinality confusion that the optimizer has.
Well,
between a single table and a join table.
Single table, join table. Well, one of the things that I mentioned is that the optimizer doesn't really have a clue about the scattering or clustering of this inter-table relationship. So whether one table is similarly ordered or clustered as the other table that it is joined to. There is not much about you can do in terms of statistics that you can generate so that the optimizer is aware of, simply because there is no statistics that describe this intertable relationship. And if you think about how many different join orders are possible in theory, then this already makes you aware of that this task is probably simply currently not really that possible, because you would need to really put in a lot of work in order to work out all these different possible combinations and their relationship. So at present, this information is not aware. If you know your data and you know that there is a particular clustering that the optimizer is not aware of, then again, these might be the cases where you have to influence the optimizer in terms of hints and other possibilities that you basically tell the optimizer you know more about your data. There are unfortunately cases where you don't have any other option than really influencing the optimizer decisions in such a very strict way.
Thanks, Randolph. And whilst we're still talking about cardinality, if you see a cardinality of 1 when you know there is much, much more, should you look for missing stats or old histograms?
Yeah, well, basically, if you see something like that, then you will probably have you are probably looking at such a single table cardinality issue, or maybe if it's a result of a join, that is something that you have to work out first. And basically, yes, of course, the first thing that you need to do is look why the optimizer does this wrong estimate. And very likely it might be a problem with the statistics. Might end up with stale statistics where you have outdated statistics. But as I said, the main point here is that even with very fresh statistics and even with computed statistics that are not based on a subset of sampling, you might have problems where the optimizer doesn't get it right. And then the usual suspects that you should look out for are these kind of expressions that are used on columns. Very often you see complex expressions using decode, case, whatever. And the thing that you need to be aware of, at that moment where you use these expressions, the optimizer is basically lost with the basic column statistics, because the basic column statistics don't tell anything about these expressions. So in very often in many cases, it is down to the problem that people use these expressions, complex expressions, in their filter criteria, and therefore the optimizer is basically lost. And in such cases, you have to do what I've this is what I've already recommended. You should review whether you really need these expressions, whether you can simplify things, where you can rewrite it in a different way. And if you are sure that you need to use these expressions, then you need to think about how you can deal with these expressions, for example, in 11G using extended statistics.
Thank you, Randolph. Well, a question here from Pawinder Singh, which carries on about histograms. So, are there any negative impacts of using histograms? He's seen queries performing bad in spite of histograms collected for highly skewed tables.
Well, the main point about histograms is that they have very limited resolution. So at present, Oracle only supports histograms that have at most 254 buckets. So if you think about what this means is that if you have tables that are very large and have a high number of distinct values in their columns, if you for instance have a 20 billion row table with 100,000 distinct values in some of the columns, and this information is skewed, then the problem is that you might end up with histograms that are not really representative for your data. So the resolution of the histogram is simply not sufficient in order to provide the optimizer with a suitable picture of the data. So very often you end up with histograms that do not really allow the optimizer to understand the data, and that is again this problem. If the optimizer doesn't understand what you are looking for, the data, that the query that you are asking about the data, then the optimizer might be in trouble and the execution plans might be bad. So there are cases with large tables, highly skewed data, that you might end up where you need to manually craft histograms in order to tell the optimizer the important things about your data. That is one of the points that this size auto feature of Oracle that has been introduced in Oracle 9i, I think, where Oracle automatically determines whether a histogram should be generated on a column or not. This is one of the points that is simply not addressed by this feature. So you can easily end up with histograms that are automatically generated by Oracle that actually lead to worse execution plans because the information is simply not representative. The cardinality estimates are simply still incorrect, although you have generated a histogram. So that is one of the problems with the histograms.
Great, thank you, Randolph. Next question from Martin Decker. Thank you, Martin. He's asking about your experience with adaptive cursor sharing and cardinality feedback. Are you aware of any issues with the latest versions?
Okay. Well, adaptive cursor sharing and cardinality feedback, just to mention this shortly, adaptive cursor sharing tries to address the potential threat of bind variables. If you use bind variables and basically want to reuse the same execution plan, reuse the same cursor, the same information, basically optimize frequent re-execution of the same statement, then you might be in trouble that different bind values for the same bind variables might lead to inefficient execution plans if you, for instance, have highly skewed data. And adaptive cursor sharing is one of the features that tries to address this. And in principle, adaptive cursor sharing has been introduced in 11G to address these problems, and it's a very good feature. But one of the problems of both features, adaptive cursor sharing and cardinality feedback, which I haven't described yet, is that both are reactive features. So they only kick in after things have gone wrong. So first things have to go wrong, then Oracle monitors the execution and compares different kind of metrics that tell Oracle that it might benefit from different execution plans, and then this adaptive cursor sharing and cardinality feedback kick in and create a new execution plan that should lead to a better performance. But as you've seen in my first example, if sometimes things can go wrong in a way where a correction afterwards don't really help you because your application is effectively already broken. So in such cases, adaptive cursor sharing and cardinality feedback cannot help because it's basically already too late. So in principle, these are good features. There are probably still bugs and quirks with them, but in principle, it's a very good idea. But you have to understand that first have things to go wrong before Oracle can actually start with a corrective action. And depending on how wrong things go, it might already be too late. And cardinality feedback is about wrong single cardinality estimates. If you have wrong single table cardinality estimates, then cardinality feedback basically feeds back the actual cardinality to the optimizer. So the next time Oracle optimizes the statement, it knows that the estimate was wrong and uses instead the actual cardinality. Another problem with these features is that they only help you with repeated executions, in particular with the cardinality feedback. The point is, if you have ad hoc queries by end users in a reporting system, then potentially every query is looking different, and then again the query can only be corrected by Oracle if it is executed more than once. And if every query is only executed once, then these features are not of any great help. And furthermore, the information is not persisted, so it's only stored in the memory in the shared pool of Oracle. If the information is aged out of the cache, library cache shared pool, then Oracle has to do the same mistake again before it can learn from these mistakes. So this is in general what I have to say about these features.
Thank you, Randolph. I've got a question here from Kirill Leusman, which is based on your first example, and they're interested in knowing how did you stop the sequel in another session without killing that session?
Yeah. Well, as I said, it's basically based on an undocumented feature, so it's not officially, it's based on an event that you need to set in the other session, and as I said, you can read the details on the blog post where I explain what I do here, and it's a very simple script that just sets a particular event in the other session, and if you are lucky and the other session is not stuck in some other code path, then it will check this event and basically cancel the operation. I also have a link to a blog post by Tyler Porter where he describes a different approach, how you can cancel a query in another session, but it only works with Unix clients, so it doesn't work with Windows clients. But it's a different approach, also very interesting to read, so I really recommend that you simply search for this term, how to cancel a query running in another session, on my blog, and you can read the details.
Great, thank you. I've got a question here from Prashant Kumar. Thank you, Prashant. It has one procedure which loads the data into a table with 6 existing indexes. CF on the indexes is very near to the number of rows, which is very high. The only thing we do to drop the indexes before the load and rebuild after the load, is there something we can do to make the CF better? Do you understand that?
Yeah, I understand that. Thanks, James. Well, the point here is that the important point is that, as I said, for the heap organized table, if you load the data in a heap organized table, then if it's a bulk load, then you can influence the clustering of the data by ordering the data. So if you can influence the way the data is loaded into the table, then you can influence the clustering. But the important point here to consider is that you've mentioned that you have 6 indexes on the table. Obviously, you can probably order your table data only in one way. So very likely you would need to find out which of these indexes you really want to have better clustering, and maybe you can influence the way the data is loaded into the table. That is basically the only way. The other only way that I'm aware of, I've already mentioned. That would mean that you basically use a different way of storing the data in the database, like an index organized table or a cluster. So these are basically the options that you have. The important point to consider is that you can only change the clustering and ordering of the table data by influencing the table. You cannot influence the clustering and ordering or the relation between the index and the table by rebuilding the index. This is also very often something that people think if they rebuild the index that then the clustering would change. But since the order of the index is defined, you in reality do not really change anything in this regard. You might end up with a different clustering factor if you look at the statistics, but then this might be simply a side effect of fresh statistics. So that is something that you need to consider as well.
Thank you, Randolph. I'm just going to ask, or we're just going to answer two more questions. I think that a lot of the questions have already probably been answered, as Randolph has gone into quite some detail when answering questions here. There's also a number of general questions about sharing links and whether the webinar will be available. As I mentioned at the beginning, full recording of this session will be available on the Redgate website. It'll also be available on allthingsoracle.com, and as that's a blog site, you will be able to put questions and comments to the video on allthingsoracle.com, and hopefully Randolph will be able to answer some questions there as well. I'll also share the link to the Tom Kite book again once we've finished with the Q&A. So on to the last two questions. Here, a question from Brian Pardy. It's quite a long one, Randolph, so please bear with me. So Brian has a query with a large in list predictate. The original query plan included the in list iterator, while an alternate plan suggested by the tuning advisor was identical except for eliminating the in list iterator. Could you please elaborate on the cost-based optimizer's method for determining whether it should or should not use an in list iterator?
Oh, well, that is something off the top of my head. I'm not really sure I can give a reasonable answer to that question. It would be something I would have to look into myself. I think there are particular issues how, as suggested, how the optimizer costs the in-list operator, and maybe it's also an issue with the cardinality estimates that result from the usage of this in-list iterator. So I'm not sure whether it's whether it revolves around the cardinality issue or more about the costing. So that is probably not sufficient information for me to give you a reasonable answer.
Thanks, Randolph. So Brian, as I mentioned, this will be up on allthingsoracle.com. I'll also share contact details for Randolph afterwards, so maybe he could help you after this session. The final question we have is from Chinir Alej. Thank you, Chinir. I hope I pronounced your name correctly as well. So it seems that the cost-based optimizer is always is not aware of the real cluster factor of the index. In this case, what behavior do we need, or what do we need to be doing?
Well, yeah, as I said, there are actually cases where the way Oracle measures the clustering factor might lead to, might not be really representative for the actual clustering of the data. And in such cases, well, the only thing that you actually can do is you need to install a manual procedure that overrides this clustering factor. In fact, the blog post that I have mentioned allows you to determine the let's say more representative clustering factor, and by getting this clustering factor right, you can use the dbms stats package to override the clustering factor that has been determined by the Garda statistics procedure.
Okay, thank you, Randolph. Thank you again, everybody, for your questions. I hope we've answered at least some part of the questions we weren't able to get to. There were quite a lot of similar themes. So again, due to Randolph's very detailed answers, I hope we've covered quite a lot there. Thank you again, Randolph. I've just put the link, or the URL rather, it's quite a long one, I'm afraid, where you can download this Tonkai ebook. I will also put this will be easily accessible from the Redgate product pages in the next few days as well. So if you haven't got time to jot this down, you just visit Redgate and navigate your way to one of the Oracle tools. There will be a link to this book there as well. Okay, so before we go, here are the contact details for Randolph and myself. Obviously an email there. Please check out Randolph's blog, oracle-randolph.blogspot.co.uk. A huge amount of information there and a lot of further reading around this topic as well. My contact details, as always, my email address for Redgate. Please follow me. My Twitter handle is @allthingsoracle, and also please feel free to connect with me on LinkedIn as well. As I mentioned, a full recording of this webinar will be available on the Redgate website and on allthingsoracle.com. You can find this particular webinar and also details of our next webinar at redgate.com/oracle-webinars, and the next webinar is being presented by another member of the Oak Table, Karen Morton. This is on Tuesday the 8th of May. It's how to gather SQL resource consumption metrics in Oracle. Another great topic here which will really help you with your Oracle performance and performance of your queries, particularly how the SQL that you write will affect your queries. So I'd just like to say thank you once again to everybody for attending, and of course thank you to Randolph for presenting a great topic in great detail. I hope everybody has benefited from today's session.
Yep, I hope so. Thanks. Thanks for attending.
Okay.
Bye.
Thank you, Randolph, and I look forward to seeing everybody at the next webinar on the 8th of May. Thank you very much, and I apologise if we haven't had time to get to your questions, but hopefully you will be able to get some answers on allthingsoracle.com when I post the video there. Thank you once again, and have a nice day.